Welcome everyone. Thank you for joining us for the latest episode of our Gleeble webinar series. My name is Daniel Quigley. I'm the Director of Business Development and Marketing here at DSI. As always, we hope you, your families, and colleagues are all staying safe and healthy. We have over 300 people registered to attend today, and looking through the attendee list, we have some of the best research institutions and manufacturers in the world that are represented here today. So as always, we're grateful for your time. We're also honored to help you in the important work that you're doing, and we'll endeavor to make this time valuable for you. Over the past 8 weeks, you've been hearing from members of the DSI team, and I imagine you're getting pretty tired of just hearing our voices, perhaps particularly mine. So today I'm happy to introduce a guest speaker. We have Dr. Carl Slater from the Warwick Manufacturing Group at the University of Warwick in the UK. He'll be presenting a handful of case studies and share some best practices he and his team have developed using the Gleeble. The Warwick Manufacturing Group currently operates a Gleeble HDSV40, a Gleeble 3800, as well as torsion and strip annealing mobile conversion units. And I've had the opportunity to visit their labs, and they are quite impressive. As always, our goal will be to keep this webinar to 1 hour or less. If time allows, we will have Q&A at the end of the presentation. If you have questions for Dr. Slater, please submit them using the chat feature here in the webinar. We will probably only have time for a few questions, but if needed, we can connect you with Dr. Slater for an offline discussion. Video of this presentation will be available online soon. You'll be able to find a link to this video as well as videos of past webinars by going to our website, gleeble.com, and clicking on resources in the top navigation bar, and then click on webinars. That'll bring you to a page where you can view past webinars and sign up for future webinars. I'm excited about next week's session. We have Dr. John Lippold, Professor Emeritus from The Ohio State University. Dr. Lippold will present using the Gleeble to study cracking and weld. Now I'd like to hand this presentation over to Dr. Slater. Carl is a senior research fellow in the Advanced Steel Processing Group at the Warwick Manufacturing Group at Warwick University, and he's been working with the Gleeble system for over 10 years. Carl, thank you for preparing this presentation, and I'll hand this over to you.
Thanks, Dan. Can you hear me okay?
I can.
Fantastic, thank you. Well, welcome everyone, and thank you for dropping in on this session. Like Dan said, my name is Carl Slater, and I'm going to go for you a brief introduction into sort of WMG, what we're about, some of the equipment that we have, and then how we use the Gleebles within our practices, and I'll give you a couple of case studies there. If some of you are new to Gleeble, then you might not be aware, but we used to run these user groups that run every couple of years, but we haven't been able to do that because obviously the COVID. So I think this is the next best thing, and it's a good opportunity to share best practices and just to talk about it, because everyone benefits if we all use the Gleeble to their potential. So hopefully that gets some of that across.
Carl, it looks like you might be muted.
Sorry, I don't know how that happened, but yeah, we go. I'll forgive you if some of you don't know WMG, because we're quite new. So the Steel Processing Group, we got our own building in 2016. We're located in the central of the UK, and we're consisted of the head of our group is Claire Davis, and then we have 3 academic staff underneath there in Prakash, Michael, and Zushu. We have about 5 senior research fellows, 12 research fellows, and about 25 PhD students, all working on steel. So this is quite a large group, all focused on steel, obviously all housed within one building. We work with loads and loads of companies. You can see just a select few here. These range from primary steel makers all the way down to sort of end users or sort of subsidiary companies, going from casting to automotive to forgings and the likes. Like I said, we're quite fortunate. We got a building all to ourselves, so we try and if any of you are able to come and visit, I'll give a tour, and we'll try and give you a tour in the order of what we make steel in. So we start off with casting and high temperature processing. We can then go through to characterization, NDT, and microscopy, and hopefully the idea is that samples can be made and characterized without ever leaving sort of a 5 meter footprint, traveling 5 meters. So like I said, we try and do the whole process in one roof, and I think that's the best way for me to explain the equipment. So if we start off right at the very beginning for primary steel making, we have this gas exchange furnace, and Zushu, who runs this suite of equipment, his emails down there. And really what we're looking at here is mimicking things like blast furnaces, baths, and then taking that to the next level and seeing what's the next generation in primary steel making, low carbon, low energy steel manufacturing, which is really hard, but that involves incredibly high temperatures and all those gases that you really don't want to do risk assessments for. So pure hydrogen, carbon monoxide, methane, and mixing that with these high temperatures. But with a gas mass spectrometer on the exhaust and really heavily controlled gases going in, then we can really see how the gases evolve during steel processing, which is really critical. We then come down a little bit and we've got the confocal microscope, and this lets us look at how solidification occurs. So looking into dendrite arm spacing, the solidus, the liquidus temperature, when inclusions form and how they agglomerate, any second phases that may form, peritectic reactions. And once we've got a bit of information about that, we can then go into actually casting. And for that ourselves, we typically use a VIM. 10 kilos is the sort of maximum that we typically make. That we find that's a good amount for people for a PhD student to have a bespoke alloy for their project and to carry through for multiple tests. But within this, we can instrument molds. We've got a gas quench system for reactive gases. So one of the particular projects I look on is near net shape casting, and it really lets us explore that possibility. We then come down to the Gleeble systems come next, and in the middle there you can see a picture of me hugging the Gleeble after 3 months of not working with it. So I'll talk about these obviously in a bit more detail, but as Dan said earlier on, we've got HDS V40, we've got the 3800, but we've also got the torsion and strip annealing MCUs to couple with that. If we need slightly larger samples, then we want to do some rolling. So we've got the hot rolling mill here, and we can typically roll from about 30 mil down to 3 mil hot, and then we can cold roll down to about 1 millimeter. And this is much better if we want to get large samples. If you're doing whole expansion tests, which the samples are not small, then we need to go through this route. Going into the cooling phase, then our NDT starts really joining at this phase. So we've got a fairly large NDT group, and they use a range of sensors to look at how can we get information about the microstructure without actually cutting it up. Is there anything that we can do to feed back to earlier up in the process to really improve the processing parameters? Can we measure things like phase fraction, residual stresses, recrystallization, all without cutting the sample up? So a lot of work's gone into there. It's absolutely not my specialty, but there are plenty of people in the group that it is. And then we go into characterization. So we have a range of equipment, a huge range of SEMs, TEMs, high temperature in situ bending, large scale mapping on the XRF, like you can see on the top left there. This really gives us the best information about what we're producing ourselves and how to exploit that. So typically, if you were to make a cast and take it through all these processes, we're talking about 4 to 5 days really. And one of the key factors that we're really keen on is that we don't want to just produce alloys. We don't want to just say, here's a new alloy. We need to make sure that it's commercially viable. And to do that, we also need to benchmark it. So the way that we process it in the lab may be different to how it's, well, definitely different to how it's commercially processed. So we need to benchmark it. What do we need to do in the lab to make sure that what we're producing could be upscaled? And I'll give a quick case study here. So this is a dual phase steel. Those of you familiar, it's got 2 phases. You've got your ferrite and your hard martensite phase, and it gets a lot of its properties from its grain size, its band spacing, and the volume fraction. So we've got those here for this particular steel. So we know that we want to replicate this particular grade. So to do that, the band spacing inherently comes from its segregation pattern during solidification. So we put that in the confocal microstructure, and we get an idea about what the dendrite arm spacing is as a function of cooling rate, because that's one of the big key factors. So we can do that. For this particular case, it agreed well with literature. In other cases, there aren't literature data available, so we have to rely on the confocal data entirely. We then go on to a simulation, so we can use very different molds inside the VIM. So on the right hand side here, you can see what the cooling rate of the cast would be if we were to cast it into different mold thicknesses, so anywhere between 10 and 50 millimeters. But actually we care about the cooling rate only through the mushy zone. So this is what this graph is showing here. So we only take that between the solidus and liquidus. We then apply the dendrite arm spacing equation that we got from the confocal microscope, and we can apply that here. And then finally, we know that a 10 millimeter sample will need to be deformed a lot less than a 50 millimeter sample for producing your standard automotive 1 millimeter sheet. So if we divide those values by the thickness, then we've got this final band spacing values that range anywhere between 9.5 micron all the way down to 3.5 microns. And from the initial picture, we can see that we were aiming for about 5 microns. So for this particular case study, we would choose a 30 mil mold. So we cast it. We do a small amount of upset rolling just to get rid of any sort of residual porosity and just take it down a little bit. We then produce Gleeble plane strain samples. So this really gives us the really high level thermal control during the processing. So the roughing and the finishing, we can put all into the plane strain sample there. And then once we have the plane strain sample, we can then machine it, make it into a flat rectangle, and then we can cold roll it. This now gives us a large sample that we can then get full tensile specimens out of. We can take subsized Sharpies if we don't deform it quite so much, and even some hole expansion. So once we have the cold rolled, we then can do intercritical annealing and final tensile testing. And you can see here that our sample sits in nicely within the distribution of that is commercially produced. And then on the right, you can see the stress strain curve and how that matches. And that is all down to the fact that we've had to match the industrial process in terms of dendrite arm spacing, in terms of the amount of production that we give it. And so we've got the complete run through there. And then once we have confidence here, that really lets us then do academic studies. That really lets us do a deep dive in some of these individual areas and have confidence that when we change a certain parameter, that we will be seen in full scale production, because there's a difference between us seeing differences on a lab, but then it get cancelled out in the noise in full scale production. Any changes once we've done this process really gives us confidence that we can make a difference. So that was the building as a whole, the group as a whole, and how sort of it comes together with that wrap process. But most of you are here to listen to Gleeble, so I'm going to give you a couple of individual case studies of how we use the Gleeble. The first one, if we start up at as high temperature as we go, looking at inclusion deformation. So most of us know that inclusions play a really dominant role in terms of the final mechanical properties. Their impact is dictated by a lot of things like their composition, the size, the distribution, and at medium to low temperatures they're fairly well understood. So manganese sulfide we know is soft, we see it being deformed during the rolling process. Aluminium oxide is not soft, we see cracking, voiding around them. But this is a lot during the rolling process. But what role do they play at higher up the process? And for this, I'm talking about during the solidified shell or any soft reduction. Does that impact anything to do with hot shortness? This work was done in collaboration with USTB and particularly Yi Wang, and she was a visitor that came to stay with us for 6 months. And I'm going to show you some of that results now. So for this, we use a plane strain setup. You can see the video here, and what we're trying to do is achieve slightly different scenarios. So the first scenario is that we want to heat it up so we have a completely liquid core, and then we want to deform with a liquid core. Second one, then we're going to do the complete opposite. We're going to heat up and we're going to stick with complete solid, so 1400 degrees, everything's still nice and solid at that temperature. And then the third one, we're heating up to a liquid core, hold for a while, and then cool back down to 1400 where we're solid. And the video there, you can start seeing the emissivity difference caused by forming the liquid core. We still got a solidified shell, so that's what's holding it all together at this point. But you can really start seeing that liquid core coming into play. And then if I speed this up a little bit, and then we should be deforming. And as many of you Gleeble users know, that when it goes right, everything's quiet, everything's easy, and it looks nice and easy like that. However, things don't always go right, and this is, I think it's just worth showing when things go wrong sometimes. So in this particular case, I put the anvils a little bit too close because I wanted to preheat them, and hopefully start seeing liquid pouring out the side for some reason rather than in the middle. I should have stopped the test there. I didn't. Kept on going. It burst out the side. Should have stopped the test there. I didn't. And then it goes like that. But things go wrong. I think it's worth sharing it when it goes wrong, because sometimes it's easy to show the video, the previous video, and think, oh, that's a dead easy test. But actually, a lot of work goes into that. I think Yi and myself spent a good 3 months trying to perfect this technique. And in principle, I say if half your tests don't go wrong, then you're not being adventurous enough. Let's push these kits to see what they can really do. So let's go back to the test that works. So we've taken this sample, we've deformed it. We've got our deformed material. We then cut it up and we want to do inclusion analysis in that section. So we have a automatic inclusion analysis on site, so we can map very large areas. And so that's a better look into it. So here we can get information like the area, the aspect ratio, the individual composition of all of these, and then we can look at that, how that varies under the different conditions. And so if we compare just the two outlining conditions, we can see the one on the left, that the calcium oxide content, particularly in the middle of the sample where we had the molten core, is much, much higher. But the size of the inclusions hasn't really changed that much between the two conditions. But one thing that we can tell the difference is the aspect ratio. So the amount these are deforming is significantly changing, even though we're putting in the same macroscopic strain. And that's really quite key. And if we think about how these inclusions of the transformation that they've gone through and the state, then for condition 1, we're in this kind of field here. So we've got majority is calcium oxide, and we've also got a liquid steel core. Number 2, we're at lower temperatures. We've got an equilibrium steady state of calcium oxide and calcium sulfide. And because we haven't gone up to a liquid temperature in the steel, actually the transformation would be 100%. So it's far on the right hand side of the TTT curve on the right. However, the final one where we've gone up to liquid and we've cooled down, actually then we're in this kind of transition region, particularly on the TTT curve there, where you can see only a small fraction of these have changed. So we've got the solid steel, but we haven't fully transformed from the calcium oxide, the soft calcium oxide, to the harder calcium sulfide yet. And that's really what's dictating here, is that we've got a difference in balance in each case between liquid steel, liquid inclusions, solid steel, solid inclusion, and solid steel with liquid inclusions. And really, to understand how these properties of these inclusions behave, you have to go up to liquid temperatures. It's hard, it's a tough one, and it takes a long time. But if you really want to get the morphology, if you really want to get the timings right to simulate casting, then you have to go to this liquid core. Once we have that information, we can start getting a bit of information about the mechanical properties, and that's what the work that's going to be coming next. Is that once we have an idea about how much it's squashed, then we know what the hardness should be, what the strength of that inclusion should be. If it deforms not very much in a solid matrix, then we know that it's got a much higher strength than the steel, and the steel preferentially deforms around it. So this is just some initial results. We're still going through them now, and Yi and myself will be doing some more work now that she's back in China, and hopefully this will progress more. And we should be getting a paper out on this fairly soon. So I guess watch this space. The next exciting sort of case study I want to portray is the near Solidus forming. So this is some work that I've been working with the University of Mondragon with, and this is really next generation future forming. We're looking at deforming materials, really target temperatures. So we're looking just below the Solidus temperature, So for some steels, this could easily be above 1400, way beyond what conventional forging companies will look at. The strain rates that we're talking about are in the hundreds, and strains 5, but even higher could easily be possible. And what we need from the material at this point is a nice balance between the strength. We want to get good strength so it holds together, but we need to be able to form it without cracking, but we also need to form the right amount of liquid or right amount of softening to lubricate itself while it's forming these complicated shapes. And we've also got a KTP, which is a knowledge transfer partnership with WH Tildesley, who is looking at upscaling and commercializing this technique. So here's just a couple of simulations from my PhD student, Andrea, whose email's down at the bottom. And as you can see, it's not an easy strain profile. We're not talking about conventional 20% just simple uniaxial compressions that we're talking about here. If we really want to simulate this, we're talking about very, very complicated patterns. So when it goes right, we get a really nice consolidated part. We get excellent grain size reduction. So we're starting off at grain size easily up at 200 microns because we've gone to such high temperatures, but we recrystallize down to very, very small grains, in some cases down to sub 10 microns. The forces that you need to compress these parts now suddenly reduces incredibly to about 200 tons compared to the 3,000, 5,000 tons that you need to forge it conventionally. Because we're not heating it up so many times, because we're not forging it and having to go back into a reheat furnace and back and forth, we're saving quite a lot on time and energy and material. And when you're at those high temperatures, then the materials tend to become much, much softer, and so we can make much more complicated shapes than in conventional forging. When things go less right, I originally put when things go wrong, but I think I prefer to go with less right. We can form excessive liquation at the grain boundaries. This is not particularly great. We can get partial dynamic recrystallization. You can see by the EBSD trace on the top right. We can get porosity, or if we go too cold, then we get freezing and underfill. So to really dictate what the process window is for an individual material or a component, then we need a piece of equipment that can really controllably give us the deformation mechanics of individual materials at these ultra high temperatures, strain rates, and give us confidence in where we should be targeting. And for this, then we don't really go much further than the HTS. So again, got a simple plane strain setup there, but you can see here that we can do temperatures quite controllably, get flow stress curves all the way up to 1390, and here you can see that we get the ductility drop here. So we get to the point where we get null ductility, and that agrees quite nicely. So we expect to see under equilibrium conditions with no segregation, we'd expect this material to start at Solidus about 1410. So it's not just the flow stress that we care about, but we also care about adiabatic heating. Because of the high strain rates, because of the precise temperatures that we're involved with here, we're really looking at the corners, just producing that small amount of liquid, ideally, just to help us lubricate. So we use the Gleeble again for that. So it's a fairly simple setup, but again, it took a while for us to really perfect the technique. But the reason we need to do this is because literature values are very varied. It's a very, very hard thing to measure adiabatic heating. And in literature, you can see that there's values somewhere between 10% and 90% of the energy is turned into heat. So we need more precise values than that. So use the Gleeble. So the simple sort of process here, we typically heat within 50 degrees of the deformation temperature pretty quickly, and then slowly get to the deformation temperature. We turn the heat off or the power angle off if you use that term. We deform, we wait for half a second, and then we bring back in the power to give us a nice controlled cooling. And you can see a typical curve on the right hand side there. So we can do that during all of the different deformations. And then you can see here for two different materials, the Invar typically is about 50%, whereas we drop down to about 30% for the 42 chrome moly steels. important for us to do that. So that's quite, particularly again, these high strain materials, 30% is still a significant amount of energy that you're turning into heat. So once we got all this, then what are the possibilities? I don't think any of us between us and Mondragon are happy just to make conventional parts on near Solidus. What's the next step? What can we do that other people can't? Well, luckily, hot off the press, I guess, just before we went into to lockdown, we decided, well, let's make a duplex part. Let's make a component out of two materials. So here we've got a stainless steel outer tube with a 42 chrome moly inner. We thought this was a good one because the automotive industry doesn't really adopt stainless steel because it's an expensive material, and really you only need stainless steel on the outside because it's there for corrosion resistance. So let's see if we can make a part that has a stainless steel outside but with a standard automotive forging steel on the center. And we did. So this is an XRF trace just to really highlight how the two materials are deformed together. And as you can see, we've got the stainless steel fully encapsulating the 42 chrome moly. So from a corrosion point of view, the outside shell should behave as if the part was entirely made out of stainless steel, but we've still got a good 50% of the material made out of the cheaper 42 chrome steel. So that's really exciting. This process, I guess, is very similar to a friction weld or rotary linear friction welding, where instead of the flash going outside the material, you can actually see the flash is actually formed inside and actually giving us a larger surface area, giving us a larger contact area between the two materials, and should be a better strength. We look into the microstructure of this, then depending on the different locations, we've either got a very flat surface or a rather serrated surface. We need to do a bit more work just to see whether, which is better in terms of mechanical properties. Is it better to have the larger contact area of the serrated one, or does that add to stress concentrations? But what we don't see is porosity, and we don't see intermetallics. If we do an elemental profile across one of these interfaces, we can see we get a really good amount of cross diffusion, much more than what you get in a friction weld, and this agrees quite nicely. So if we go to thermodynamic predictions, we found that if we've got a cooling rate of about 12 degrees a second, then we get really nice profiles for our chromium and our nickel. So we've got every reason to believe that these interfaces are very, very strong, and should give us a fully working part. This is the first one that we've done, but quite excited about the results, and we've got a paper under review at the moment, so hopefully you'll see that in the future. So the next stages for this, really, Mondragon and ourselves are making more and more complicated parts all the time, and the work really will focus on how can we get the most out of the microstructures for these parts, how can we optimize the amount of dynamic recrystallization, how can we get the best material properties as well as getting the shape for these really, really complicated forging processes. I'd love to be producing more of these duplex parts. I think they're fun, I think they're exciting. It's really something that other processors can't do, but that will come with its own challenges. But for the foreseeable future, the HDS is definitely going to be the port of call for that. So we need to get more information about these materials and how they behave at these temperatures, and the HDS is definitely the way forward for that. Okay, and the final case study, I know that Fulvio has given a couple of talks about recrystallization and deformation, so hopefully this sort of piggybacks off that a little bit. And this is a more conventional, so we've come to much lower temperatures now, much more conventional hot rolling temperatures. We all know that segregation exists. It's almost impossible to get rid of it entirely because it's expensive. So really the question is how much segregation is too much? How much do we need to really homogenize it? And what are the knock-on effects? So if we had a certain amount of segregation, what can we expect to change? And one of the things that we know is that when we have manganese segregation, for example, and manganese is a pretty good solid solution strengthener, that we're going to have these local mismatches in strength across the sample, across the strip. So what's the implication of having that? So to do that, we've got two steels here. So the segregated sample is as received. It's a 20 man chrome 5 steel, an automotive gear steel, and that's how we got it off the shop. We took that and then we homogenized it for 48 hours at 1250 to really get rid of the segregation as much as possible. But obviously the grain size is going to be huge at that point, so we went through 4 normalization cycles, taking it austenite ferrite several times to get the grain size back. So now hopefully what we've got is two materials, two strips that have exactly the same composition, exactly the same, well, pretty much exactly the same grain size. The only thing that's different is the segregation. And you can see those there. So each of these was put in the Gleeble. So we want to do a just a 30% upset deformation, 900 degrees, and 0.3 strain. Really standard test. We want to put this right in the heart of all the recrystallization work that's been done by Duttercellers and anything like that. We want to be nice and predicted. And as you can see here, if we do a 30-second hold after deformation, we've got very different microstructures. The homogenized sample, we've got a very unimodal microstructure. It looks to be fully recrystallized. Whereas the segregated sample, we've got these really stubborn large grains. You can see from the grain size distribution there, it's not even. We've clearly partially recrystallized. So then if we do some more samples and we left it for different periods of time, it looks like we're pretty much 100% recrystallized after 60 seconds, but we're definitely 100% recrystallized after 300 seconds. So clearly the kinetics involved in the segregated sample are much more stubborn than that of the homogenized sample. But not just the kinetics, the actual final microstructure is actually very different as well. We can see here that the homogenized sample has got a finer microstructure, both in terms of the mode grain size, which we know should influence the yield, but also the maximum grain size, which will inherently affect the toughness. So we're not just getting a difference in the kinetics, but we're seeing a real tangible difference in the strength of the material as well. So if we try and understand this, then we've got the classic equation for predicting grain size of static recrystallize here. If we apply it to the homogenized sample there, you can see in the difference. If I just get the you see in the difference here, we predict the 10%, the mode, and the larger grain size in the distribution pretty well. That's not bad for saying that we just got some fitting parameters here. Then if we look at comparing that to how it predicts it for the same fitting parameters, because after all, those fitting parameters are material specific and we've actually got the same material, actually the differences now are incredibly different, with the D90 being almost half. It's incredibly poorly predicted. So we want to know why this is. So to do that, we want to do some simulations. And so we've got the XRF trace. We can do that of fairly large samples, so we can actually do that of a full Gleeble sample. So we can section a Gleeble sample in half, get the full map. And then we want to apply the strengthening coefficient. So manganese for ferrite is fairly well known. You can see that in the volumetric change of the system because of manganese. For FCC, it's fairly similar, the strain it causes on the lattice. So the coefficients aren't so well known for austenite, but for this, we've assumed that it's be the same. Carbon's a little bit more difficult. It's there, but it's harder to pick up. We can't pick it on XRF, so we have to predict it. We know that carbon prefers to move to high manganese regions. So if we do this basic thermodynamic prediction here, so we've got a manganese segregation, we haven't got a carbon segregation to start off with, and then we leave it for a certain period of time for it to homogenize, and we can see that the carbon preferentially moves to those high regions. Okay, we've not had a huge difference. We've only got 0.006 weight percent difference in the two regions, and that constitutes about 4 megapascals. But it's important to do. It makes the modeling more complete. So as you can see here, we've got the full Gleeble sample where we've got the strength map that's been dictated by the actual composition. And we can see that for a 0.3 strain, the segregated sample shows a much broader range of internal strains, local strains, compared to the homogenized sample. and we can summarize that here. So in the homogenized sample, we're only seeing strain variations within the sample of 0.26 to 0.35 strain, but in the segregated sample, we're seeing strains all the way up at nearly 0.5 and minimum strains of about 0.2. So if you remember from the kinetics, then we predicted, well, we measured that the homogenized sample finished recrystallizing after 30 seconds, and the segregated sample one maybe around 60 seconds. Then we can see that on this bottom row here, clearly fully percent recrystallized, even if we take the lowest strain. So if we assume that the lowest strain is the last to recrystallize, then clearly we're still within 30 seconds here. But for the segregated sample, we're around 60 seconds, which is what we measured, and that's starting to give us an indication that we're looking along the right track. But then let's look at the same thing that's the kinetics, but let's go back to the grain size. Well, again, if we look at if we focus on the D90, because that showed the biggest difference, for the homogenized sample, we were showing a 12% difference, but we've actually managed to improve that. We've improved something that originally was quite good to something that's now very good. And we've gone from this 93% deviation to all the way down to 23%. So we're not quite telling the whole story, but we're getting there. It's starting to give us an idea about where this deviation is coming from. So to conclude this case study, then we've shown that segregation really has a real tangible influence on the recrystallization kinetics, and you need to do this combination of Gleeble tests and sectioning and homogenization to really get a feel for how much it's impacting. And that's one thing that I must say that we don't see a huge amount of in literature. When people are using recrystallization studies, they say this is the material that we used, but what's the segregation condition? Is it fully homogenized? What is fully homogenized? And that really muddies the water for all these fitting parameters or these recrystallization kinetics when we're trying to do literature searches. Most of this is come from the manganese segregation. In this case, this is the one that we've measured. I must admit that we also did it for chrome and nickel and the other alloys, but their contribution is much less for this particular steel. And the strain difference is because of that solution strengthening is really causing these local differences, which is having a knock-on effect onto recrystallization kinetics, but also the grain size. But I mean, I've not gotten into too much detail here, but to be able to do this, then you really need to have good finite element modeling simulations of your Gleeble. If any of you have ever cut open a Gleeble sample, you'll see that the barreling causes real knock-on effects on your strain through thickness. And you have to really couple that with a good microstructural, good finite element model to tell you what part of the sample you should be looking at to be able to get this level of detail out of it. I'm more than happy to talk to you individually about the modeling that we do to help support that activity. And I thought I'd just finish off with a couple of future work. So some things that we've got a couple of ideas on and what we take on. But as you can see, all this work that we've done for the case studies has been part of collaborations, and that's where I think a lot of our strength is, and I certainly open up the conversation with a lot of you guys to collaborate, to work together, and to really push forward some of these ideas. The first is an in situ rolling rig inside the 3800. This is Mark 1. We are on Mark 2 now, but I didn't have a video of that, unfortunately. The idea being that at the moment we use uniaxial or plane strain or torsion to mimic rolling. Why can't we use small scale rolling to mimic larger scale rolling in the Gleeble? So we've set up the 3800 here. This is just showing it cold, but we're now working on that being hot, to have motorized rollers, to look at oxide breakup, to look at the shear loads to give us that difference in shear through thickness. The one on the right there, so coupling this with the work I was talking about oxide deformation earlier, then actually 3-point bending becomes really important in terms of being able to figure out whether a particular material is castable. So when we're developing new grades, when looking at next generation TWIP or TRIP or electrical steels, anything that is likely to have breakout, and really we're talking about 3-point bending with a molten core. What is the hot ductility of this? What is there any hot shortness? And be able to get some information about that. I believe the HTS is in a perfect position to be able to help that out. So I welcome any ideas on that. So that comes to the end of my my presentation. I'd like to thank DSI again for giving me the opportunity just to present some of the work. Hopefully that gives you a bit of a taste for what we do, and I welcome any questions.
Carl, thank you for presenting. It was great. We appreciate it. There are a handful of questions here.
Sure.
We've got a few. I'll just kind of lob them over to you, and you can take it from there. One question was in regards to the liquid core reduction. So in that example, how are you managing the liquid content? Can you truly rely on the emissivity difference on the solid surface?
Oh no, so the emissivity from the surface is just a nice happenstance. So I tend to put the thermal imaging camera on everything we do. We certainly don't control it. So part of the long process of setting up this technique was a lot of interrupted trials. So we've got a very known microstructure to start off with. We heat it up, we hold it for different periods of times, we quench it, and we're able to look at the microstructure at where the melt pool was. So what's the repeatability of that? How many? What's the size of that with time and temperature, and how much control we have over it? So the size of the melt pool is entirely dictated by interrupted trials and in situ measurements. The thermal imaging camera is just nice for presentations.
Okay, thank you. We had a question about validation. It says, I assume that hole expansion and tensile testing alone are not enough to validate your physical simulation cycle with full production. For DP steels, the TMCP cycles are of utmost importance. So can you do interrupted accelerated cooling in your lab as well?
Yeah. So the good thing about working with small samples is that they tend to cool pretty quickly. So we have entire control over it. So the process itself is quite manual. So whether we're doing casting, we can use water-cooled molds. If we want to do hot rolling in the mill, whether doing it on the Gleeble, we can always use a quench medium. So understanding the individual parts in more detail, quenching is an absolute must. I completely agree with that. The idea initially is to say, what do we need to do to be able to get the same value, the same tensile properties? But then when you do the deep dive, then quenching and interrupted is absolutely key. Absolutely right.
Okay, thank you. I think the failed test that you showed was actually pretty interesting, and that may have spurred this question. It says, question about near solidus forming. What type of lubricant should be used at the die and workpiece interface? Is there a sticking problem between the workpiece and the die? Our team typically uses graphite foil with a nickel-based barrier. Do you do this as well, or have you experimented with other methods?
So if we're talking about the actual Gleeble testing, then the plane strain setup that we have in the HTS doesn't actually require any lubricant or any interface there at all, because the HTS works slightly differently. And for those of you that don't know the HTS too well, then the electrical load comes through a different axis than what the mechanical load does, as opposed to in the 3800 where your contacts are you have the same contact for electrical and mechanical. So your anvils don't carry a current. They stay far away until they're actually needed for deformation. So for that case, then we don't. For high temperature uniaxial, then it depends depends what the material is. So we tend to use tantalum foil. I will typically use 2 layers of graphite foil, then a tantalum foil on the bottom, because heat rises and you need to get a little bit extra resistance in the bottom one. But it's a delicate balance, really. It really depends on how good your atmosphere is, how worn your anvils are. If the question was more directed to the actual process, then the chaps at Mondragon are in a much better position than myself to talk about the lubricants for that. But I know in the forging world, lubricants are certainly a hot topic, and I'm sure we're looking into it.
Yeah, no pun intended. Actually, that was the follow-up question, referring to the production. So we'll pass on that one. And I think you also answered a question that I was going to ask you. I think a lot of our customers aren't familiar with the HDS V40. So when you showed plane strain testing, for example, it's a bit of a different setup. So you kind of just did describe it, but would you mind maybe talking a little bit more about how that setup is? That obviously is a much larger specimen than our typical, what we call large plane strain or small plane strain, which is
Sure.
more of a block.
Yeah. So for us, a typical plane strain sample. So the sample is held horizontally and it's gripped either side with the copper grip. So very similar to how you imagine a 3800. And that gives you the nice constant electrical load. So you have your thermal profile going across it like you would normally. They're water cooled. So that length for us is normally about 160 millimeters. A typical sample height, we're talking about 10 millimeters, and then anywhere between 20 and 50 millimeters wide sample. So you heat that sample up, but contrary to the 3800, your actual loading anvils are above and below your sample. So you've got a completely different plane for your mechanical load. So it's quite nice. You're backed up. You're really far away. In some cases, I keep the anvils fairly close to the sample just to get a bit of heat, so there isn't too much cooling once the anvils hit. And it also means that you can have this huge run-up space. So the strain rate you get out the gap, out of the traps is really, really high. So easily get 100 per second, and you get to that speed before you even touch the sample. So it works slightly differently. It's quite different to get your head round. I wouldn't say that one is better than the other. We're quite fortunate in that we have both. So, it's just a different concept. Certainly for these ultra high temperatures, then I would always use the HDS, because the benefit really is that the bit that's at the temperature that you're going to deform, nothing's touching it while it's heating up. So you could have it at 1400, 1450, even getting closer to 1500, but nothing really is touching it when it's at that temperature. And then you can come in for that brief deformation and then do your cooling.
Right, and there are only a handful of those HDS V40s out in the wild, so I think the testing you're able to do with it is fairly unique.
Yeah, and that's one of the we've only had this system really up and running for 3.5 years, so there isn't a huge amount to go on. So a lot of this stuff has been trial and error ourselves. I mean, it's fun in parts for sure, but yeah, it's really just getting the most out of it ourselves, because there isn't a huge amount of literature out there where they've used this system.
We got time for a few more questions here. One question was, how was the microstructure captured during the hot deformation of inclusions? Was it simulated? So I think you mentioned that you have some equipment that can do that. Can you talk a bit about that?
So during deformation, we can't. So what I showed there is the quenched microstructure doing inclusion analysis afterwards. The in situ observation of microstructure was done in the confocal microscope. For that one, we can't really do liquid deformation. So we can either do solidification under no load, or we can do some deformation, some tensile or some compression deformation, but we were really kind of limited to 1,300 degrees there. So those two aren't. So again, coming back to the question earlier about quenching, is that, yeah, most of what we do is interrupted test, quenching, and then doing cold characterization.
Great, thank you. Actually, we have a few questions were about that, so I'll skip those and you just answer them. Have you looked at the collaboration of WRT, crystal plasticity modeling of compression to simulate Gleeble?
No, I haven't. I've got some colleagues back at University of Birmingham, where I used to be, that are excellent at this. I would love to collaborate on something like that. It's certainly not an area of specialty for myself, and I think it's certainly needed to really get to the next level of simulation, to get the next level of prediction of some of this, that's going on. So no, I haven't, but I'm certainly open to the possibility.
Great, and I think one more question here. It says, will the difference in microstructure between the homogeneous and the segregated material become less after multiple pass deformation with much higher total reduction? If you want, I can repeat that.
The difference is, I mean, for the dual phase steel, it's really down to things like the cooling rates, and the intercritical annealing and things like that. For the 20-man chrome 5, then the microstructure was actually very similar. So that is a martensitic steel. It's fully martensitic. You would expect a slight difference in the tempering response, maybe the MS temperature to change a little bit, but the levels of change that we're looking at in these segregated samples on the 20-man chrome 5 would not be that much. If you're talking about a dual phase steel, yes, you still get a large difference. You're really changing your phase stability in your segregated rich regions, in your segregated poor regions. So the scale of what that inhomogeneity will be different with different amount of reductions, but you would still get the inhomogeneity.
Thanks. I guess last question, and I had this question as well. It says you had mentioned aspect ratio, and how do you measure that? Is that
Okay, yeah, so it fairly simply, I mean, particularly because we know the direction of the deformation, so we're looking at the x direction over the y direction on an SEM. We're just measuring those two lengths and seeing that, and then for a known deformation of 30%, we know what a sphere should deform into, so we have an idea about what it should be if it was perfectly deformed, and then the aspect ratio is that ratio between the length over the height.
straightforward? Thank you. I think we're running out of time here for questions. I'm going to take control back over here. I'm going to share my screen. I just wanted to, again, Carl, thank you for the presentation. It was great. I think it was really interesting, the work you guys are doing, and certainly the collaborations that you've developed are you have a lot of great organizations. So it's impressive, and we certainly appreciate you sharing with us, preparing the presentation, and taking time today to present to the group and answer our questions. If anybody does have questions for Dr. Slater, if you need his contact information, it was up on the screen, but please feel free to reach out to me or our team, and we can connect you. I put up some contact information on the screen here. Again, I just want to make sure if you have technical questions about Gleebles in general, please feel free to contact our service team. The best way to do that is to email service@gleeble.com. And one more plug for our customer service portal. If you go to the resources link at the top of the page in our Gleeble.com, and then click on customer service portal, users can create an account. There's a knowledge base, as well as you can create a support ticket, which is, again, the best way to get support and make sure someone will get back to you quickly. If you have any questions about the Gleeble, how it can support your research, please email me or any member of our team. My email address, everybody should have it. It's dan.quigley@gleeble.com. I can point you to the right resource. Parts, consumables, upgrades, it's parts@gleeble.com. I think most Gleeble users know David Jacon, or we call him Jake, and Susan Castagne. They are both happy to help. And also parts of the world that you may know, Mark Ruggieri as well. He's certainly a resource for parts, consumables, and upgrades. We always want to hear what you guys are working on. Research@gleeble.com. If you can email us your papers, let us know what you're working on. Again, a lot of times people will come to us and ask about if anybody is working on this particular application, and it's nice to be able to point them in the right direction, and that can hopefully facilitate some collaborations. So let us know what you're working on. Again, that's research@gleeble.com. And then any basic questions, of course, info@gleeble.com, and we'll get you to the right person. Time is up. Again, I want to thank you all for joining us. We appreciate your time. Please do stay safe and healthy, and have a great day.